us to have George Wong with us today. He's a member of the Institute for Advanced Studies and an associate research scholar at the Princeton Gravity Initiative. His studies mostly related to high energy astrophysical processes, especially in the context of the observational signature of black hole accretion. And I recently got his PhD in 2021 at the University of Illinois in Urbana-Champaign. And today he's going to talk about probing the black hole jet connection. Take it away.
Thank you, and sorry about the delay for starting. Okay, so my kind of day job has been to think about black holes in kind of an observational context, but I'm a theorist or a computational theorist. And so I wanted to spend some time talking to you today about a question that I think is particularly interesting: this observational signatures of connections between black holes, supermassive black holes, and relativistic jets. And so I've divided my talk into approximately 3 parts. So in the beginning, I'll provide a one-slide observational motivation for what I think is interesting, and then go into a bit more detail about how I actually do all of my experiments using numerical simulations and so on. Then in the middle part of my talk, I'll give a description of why I think this problem is particularly challenging. So there are various theoretical uncertainties associated with observational signatures, so I'll go over them quickly. And kind of the purpose of the middle part of my talk is to convince you that it's in fact a quite challenging problem to try and invert observations into observable parametric numbers, quantities that can help us address the quantitative connection between supermassive black holes and jets. And then in the final part of the talk, I will quickly go over why I think that even though the problem is quite challenging, I think that there's hope in the future. So as I said, I have one slide of observational motivation. Again, I do mainly computational theory stuff, but I do think that it's important to kind of ground ourselves and understand why. Also, can you see? Should I stand on the other side?
Absolutely.
Okay. Okay. I think it's important to ground ourselves and kind of understand how the problem connects to actual things that we can see in the world. So I've just shown here several images of the jet in or coming out of the elliptic galaxy M87. And there are several features of this jet that I think are most important to what I'll be discussing. The first of which is that this is an incredibly long jet, a very large jet. So here I have some scales. I put on these left panels here in terms of light years. And the takeaway here is just that whatever is powering this jet, if there's some central engine, has to be powering it for a very long period of time. And so that's observation number 1. Observation number 2 is that it's an incredibly powerful phenomenon. So we can make some estimates about how much energy is contained in the jet just based on looking at, what the overall intensity is, making some arguments about the thermodynamics required to push the gas material out of the way. So if you take those 2 observations, the fact that it's relatively long-lived, it's large, so it must be long-lived, and it's very, very powerful, then we end up with the question of, well, how can you actually produce, what is the central engine? How do you produce a whole bunch of energy over a long period of time? So those are 2 observations. And then the third observation is that certainly it must be coming from somewhere. So can we get any kind of handle on where it's coming from? And that's what I'm showing you here over on the right. So as you scan in frequency space, you look at different parts of the jet, and you can see all the way, you can track the jet emission all the way down to a very, very compact object. So whatever the engine is, it has to be incredibly small. And so again, the engine has to be incredibly small compared to the size of the jet system, very powerful and also long-lived. So how do you get this? Well, I propose, I did not make this proposition, but my explanation or my accepted explanation for how you get the jet, for what the central engine is that it's a supermassive black hole. So a supermassive black hole is powering the jet via this Blindfolded Mechanism, so 1977 Blindfolded paper. And for those of you who may not be familiar, or just to remind you, the way that the Blindfolded Mechanism works is that you have magnetic field lines that are pulled with plasma, as plasma may accrete down to the black hole. So the magnetic field lines are kind of frozen into the plasma. They get pulled down to the black hole. And then because the black hole is spinning, if the black hole has any momentum, because the black hole is spinning, it pulls space-time with it. And so the magnetic field lines that are close down to the hole get pulled with the space-time and then end up getting wound up around the spin axis of the system, black hole, what have you, and end up collimating into a pointing flux jet. And so you can make some analytic estimates for how strong the magnetic field strength is in, for example, this M87 system that we saw. And you can compare magnetic field strength estimates to what the expected Blandford-Dinac jet power would be, and it approximately matches observations. So this is a reasonable proposition for what's going on. It also occurs to me, I meant to say at the beginning of the talk, please feel free to interrupt me at any time. I'm going to kind of give you an overview of what I've been doing, so I won't be going into detail. I'm happy to talk later with any of you individually, but also feel free to interrupt me. Okay, so this is the way the Blindfolded mechanism works. Magnetic field lines get pulled down to the hole, get wound up around the hole, and collimated into a pointing flux jet. So if we want to come up with observational evidence for the Blindfold-Dinac mechanism, what do we need to do? We need to do two things, at least. We need to measure the spin of the hole, because the spin is what's providing this torquing. And we also need to measure the magnetic field. So we'll talk about what that means a bit more precisely later. But at the very least, you need to do these two things to come up with definitive evidence of the Blindfold-Dinac mechanism. Okay, so what do I do to try and answer this question? Well, about 50% of my time is spent working on codes to run numerical simulations of black hole accretion flows. And so this is the general pipeline for how I produce these simulations. You start with a fluid simulation. So a fluid simulation is just magnetized plasma. You input some properties like the spin of the black hole and what its angular momentum is, and also what the relative orientation and field strength is for the magnetic field in space. And then you just evolve it like a fluid, like a magnetized fluid in GR, general relativistic magnetohydrodynamic simulation. So that's the first step. And then the output of these GRMHD simulations are time series, which describe the density, temperature, velocity, magnetic field, and so on of the fluid. And then to connect these simulations to observations, you can add some model for the electron thermodynamics. So how hot are the electrons? What is the distribution function of the electrons? Where is my camera relative to the system, for example? And then you take that time series that comes out of the GRMHD, you ray trace it with these thermodynamics, and you produce observables like on the right here, this movie of a black hole. Of course, you can produce other observables, spectra, and so on. But this is the general picture you should have in mind. So the spin of the black hole is just its angular momentum, but the other input to the GRMHD simulation is the magnetic field strength. So I want to quickly remind everyone about kind of these qualitatively these two qualitatively different states you could have for the magnetic field. And basically it's set by whether or not the magnetic field strength near the black hole is powerful enough to alter significantly the dynamics of the accretion. And so the two cases are where it's not powerful enough, so the magnetic field just follows the turbulence. This is kind of standard and normal evolution, sane evolution. Or alternatively, it's possible that the magnetic field strength is incredibly strong near the horizon. And so magnetic pressure builds up and it counterbalances the inward ram pressure of the flow and halts the accretion. So you have a magnetically arrested disk or magnetically arrested state, MAD. And so what I'm showing you here, I'm going to end up showing you a few movies that are of this format. So I'm going to take a short time to explain what you're looking at. So you can imagine you have a black hole, say here, and you have this accretion flow that's coming in. So you might have a disk that's going around the black hole. And what we're looking at here is just a slice through the simulation like this. The black hole is here, the accretion disk is here, and this is plotting the log of density, the accretion disk, and also I'm plotting magnetic field lines on top of it. And so just to make concrete the difference between sane and MAD, over on the right-hand side of the screen, you see that in the sane case, the magnetic field is following the turbulence. It's crazy. And in the MAD case, the magnetic field is much more structured. It's strong enough to kind of have its own influence on the flow. Of course, magnetic field lines don't like to be wound up. So, the lower energy state is when you have a strong enough magnetic field, it's just ordered magnetic field. One thing that I think is worthwhile to mention here is that in both the sane and in the MAD cases, if you look in the jet region, which is this kind of evacuated purple region with lower density, the magnetic field lines are aligned there regardless of whether you're sane or not. So it's not like sanes don't have these BZ jets in principle. They totally could.
George.
Yes.
So this is density, I presume, the color.
That's right. Log density.
I'm seeing this along the axis.
Yeah.
Some excess density in both sane and mad. Is that a numerical artifact, or?
I am going to say I don't know because this is Sasha-Chkhovskoy's simulation. I assume so.
This is also Sasha?
This is also, all of this
Okay.
is code from Sasha's.
Fine, okay, so it's Sasha's code, okay.
Yes, I assume so. So what one thing that Ramesh is referring to is, of course, that when you actually look at the details of GRMHD fluid simulations, it turns out to be hard to evolve the plasma in regions where the magnetic field strength is large and density is very small. So there are these numerical floors, and I'd be happy to talk about this in detail later. But often what you find is that you end up injecting material, for example, in these low density regions. There's a whole art to dealing with that.
No, the surprise to me was, if the whole funnel had been filled with this stuff, I would say, yeah, flow. Why would it be only on the pole? And then actually there's a lower density around it, and then the disk kicks in. That's of surprises.
I don't want to speak for Sasha.
Your code doesn't do this?
It depends on, sometimes we see it. I think we should probably talk offline because I don't know how broadly applicable it is. But treatment of the boundary condition is very challenging, and fixed grids are also challenging. You might want to move to Cartesian instead of polar and so on. But let's talk about offline. So just to make it make this mad-sane distinction a bit more clear from the morphological perspective, now I'm showing you the same kind of simulation, and these are simulations now that I ran. So I can talk about them a bit more. But I'm showing you now, instead of looking like this, I'm showing you a slice in this direction. It's still log density. I'm not plotting magnetic field lines. But again, qualitatively, there's a difference between MADs and SANEs. SANEs have a disk. There's a turbulent accretion flow that falls onto the hole. And this contrasts with these MAD accretion states, where you certainly still have accretion, but now the accretion proceeds in these filaments. So it's not clear. I mean, certainly there's something that looks like turbulence here, or maybe Rayleigh-Taylor, magnetic Rayleigh-Taylor or something. But it's qualitatively quite different from the same. So MAD accretion proceeds in this kind of choppy, bubbly way. Okay. So now just to show you an example of what the observables look like in detail and what we can kind of pull out of them. So we have these GRMHD fluid simulations, and again, we put some prescription for the electron distribution function, blah, blah, blah. We ray trace it, and then at the end of the day, we get something like this. And particularly, we get something like this. And so what is this? Well, this is just a map of the total intensity on the image plane. That's what you're seeing in the grayscale. And then, of course, you can also track polarization. So what I'm plotting on here on top is the electric vector position angle, which is just the orientation of the electric field oscillations. And also the fractional linear polarization. So how much of the total intensity light that you receive, how much of that is associated with this linear polarization channel. You can look at this in different ways. So you can break it up into the total intensity, linear polarization fraction, the EVPA, also circular polarization, of course. And one thing that's worth pointing out, I believe, is that this is a high resolution observation in some sense. It's limited by our computers. So if we want a higher resolution, we got to hire, just take a little bit more time on the computer. But of course, in the real world, we have these blurring artifacts because we're observing the beam. And so there are some qualitative differences between a high resolution observation and a lower resolution observation, one of which that is particularly important is look at the linear polarization. I spelled linear wrong, but if you were to look at the linear polarization, and you look at regions where this EVPA, so the electric vector position angle, where it's oscillating wildly, then when you average all of this together, if you have electric field going this way and this way, it averages something like 0. So you have much lower linear polarization in a blurred or realistic observation compared to in a high resolution observation. So this is worthwhile to keep in mind, I think. Okay, so at the end of the day, I run a whole bunch of different numerical simulations. and produce a whole bunch of movies. So again, the input to these simulations will be the spin of the black hole, whether the overall accretion state, whether I want it to be mad or sane, also the details of the electron thermodynamics, the location of my camera relative to the system. I produced images over here, and I did a calculation, back of the envelope calculation, and I think I've ended up producing about 50 million different images of black holes, of which I have probably looked at a few thousand. Okay, and so at the end of the day, I want to connect these observations somehow back to this Blandford-Zerniak question. And again, remember, for the Blandford-Zerniak question, you want to know the spin of the black hole and what the magnetic field is doing. And so I figured, just to kind of introduce this connection between observation and these modeling questions or these physics questions, what we could do is review the EHT results. So I know many of you are probably familiar with this. It's just going to be 2 or 3 slides. But the main overview of the EHT results with respect to this Blandford-Zerniak question. So of course, it's not fully comprehensive. So looking over on the right, I've just taken a sample of those millions of black hole images. And I have selected or highlighted 2 images in particular that come from very, very different models. So I think in one case, the spin on the top is plus 0.94. So it's a highly spinning system where the accretion disk is going with the black hole. And then the spin on the bottom of those 2 images is retrograde. So the disk is going in the other direction. And the black hole is spinning at 0.5, so not as highly spinning. And the upshot here is just that those 2 images look incredibly similar, at least in my eye. And so this poses, in some sense, a modeling problem, because it turns out that the intraday variability between different observations, as coming from the EHT, for example, can be larger than the differences between 2 different models. So 2 very different models, different spins, different senses of orientation, or senses of rotation, can look very, very similar, whereas just waiting a day can make the data look very different. So this is a challenging problem. And so at the end of the day, what you want to do is you want to try and find some robust observables in your data. So say, well, okay, I know that there's some variations from day to day, but those variations all fall within a certain property class. And then you want to try and identify what those robust observables map to in terms of physical parameters.
Can you go back to that?
Yes.
So are you saying that for those 2 images right there,
Yes.
over the course of a week, it would exhibit the same temporal variability?
Oh, yeah. Well, I guess maybe I don't understand your question. So these are just snapshots that I pulled from the time series. And I selected these in particular because they look very similar. I wanted to point out there were differences. But if you were to pull the full movies from these guys, I don't know in particular what the variability would look like for these 2 frames, but I totally believe that variability could be approximately of equal magnitude for those 2 movies. But what I will say is that in general, if I pull a movie from the simulation library, right, then the amount of variability within that single frame, within that single movie, so for the same black hole spin, for the same and so on, that variability can be much, much larger than the difference in some quantified way, difference between a frame pulled from that movie and a frame pulled from an entirely different movie.
I think someone asking is that if you had the full time series, could you look at the full time series, the bottom one, the full time series, the top one, and tell the difference, or would it just be so noisy that you couldn't really tell?
Yeah, I mean, for these particular ones, I don't know. In general, I have seen movies where, for me, it's very challenging to tell the difference. But of course, variability or time series data helps you. In a few slides, I have a kind of plot of variability for different models, and so when we get to that, maybe we can come back to the question. But overall, yeah, I can pull 2 very different models and look at their variability, and depending on which measure you use, of course, they can look very similar. Right, so in the face of this challenge, what you want to do is you want to come up with or identify the robust features and map those robust features to what they mean in a physical sense. And so again, for the EHT, in the context of this Blandford-Zerniak spin magnetic field measurement, what we identified was there's a consistent sense of the brightness asymmetry. So it's brighter on the bottom left in the south east.
Yeah,
I said I'm there. Yeah, so it's brighter there, and so certainly there are variations. The position angle changes, but it's generally brighter in the bottom left. And then if you look at these polarization patterns, there's an overall sense to the polarization patterns. And I won't go into the details of how we determine what this means, but the upshot is just that the brightness asymmetry orientation is aligned with the sign of the spin of the black hole. So we don't necessarily know quantitatively how fast the black hole is spinning, but we think that the angular momentum vector is pointed away from us. And then the linear polarization measurements imply something about the structure and strength of the magnetic field close to the event horizon. Okay, but we want to do better, right? For the Blindfolded process, it's important that we be able to track the magnetic field that's in the jet all the way down to the horizon scales, because the claim of Blindfolded is that the magnetic field is being pulled by the spin of the hole. So you really want to be able to connect the magnetic field in the jet down to the horizon scales. And so to kind of address this question, I think it's important to study and understand where the emission that you're seeing is actually coming from. Because magnetic field by itself is not observable. You can't look into space and see a magnetic field line. So you have to kind of associate those magnetic field lines with something, with linear polarization, with flux tubes or whatever. And so one of the ways that I found, one of the things I found to be very useful in this kind of analysis is just to create these three-dimensional representations of where the emission is coming from the black hole. So I've pulled two examples here over on the right. So these are just the black hole images. I chose them to be relatively similar, but not completely similar. But I didn't choose them in any quantitative way. And then on the right, what I'm showing you is just the location of emission around the black hole, and I'm spinning it around just so that you can see the full three-dimensional structure. And what you can see is, in fact, there's quite a lot of variation between the top emission map and the bottom emission map. So the top emission map is for a MAD simulation. And you will recall from earlier on, the case of MAD simulations, the accretion is quite choppy, right? There are these filaments, it's not this steady disk. And so what you're actually seeing here is that all the emissions kind of coming from, I'm going to use the term loosely, kind of like the atmosphere of those filaments. So kind of like the low density structure around it, it's very, very hot. And it's crazy, this is an individual snapshot. If you average this out, it looks uniform, it looks ordered. But in any individual snapshot at a particular angle, at a particular azimuth angle in the real space can be very, very different. On the bottom, what I'm showing you is a particular sane simulation. And here, the emission is primarily coming from this kind of interface between the rotating disk matter and the jet, kind of in the funnel ball. Yeah, Tom.
These are really cool. Where is the observer in these 3D ones? Are we kind of at the top looking down?
Let's see.
I'm trying to just map some things to
Yes.
the image, like this one on the bottom is this big filamentary thing that I'm trying to associate
So
with.
that's right.
So that's from the top looking down.
At 17 degrees.
So almost it's looking down.
Yeah, so there's a line here, and there's also a line there, but it's hard to see. So it's 17.
I got you.
But yeah, that's right.
For the sane, it looks like you've got more filaments on top than on the bottom, by which I mean, is that a coincidence or something to do with lensing?
I think actually it has to do with the motion of the plasma in the sense of beaming. So whether the plasma is coming towards you or going away from you. But this is a highly model dependent thing, as I'm sure you would guess. Yeah, so I think in this particular case, it has to do with the motion of the plasma.
Interesting.
Right, but in general, this kind of inversion process is challenging in the sense of, ideally what we want to do at the end of the day, again, is to match the structural magnetic field. I'm going to keep on harping on that point. So we'd like to perform a tomographic reconstruction, take an image and somehow come up with this guy and even more information about actually the structural magnetic field. But this is a hard problem. So these are just some other frames from 3D movies, along with kind of an azimuthally averaged version of the 3D. And the point that I want to make here is that qualitatively in your minds, you should think that the emission from MADs is all coming from kind of this blobby region, regardless of what the electron thermodynamics are doing, regardless of the spin of the black hole. It's all kind of coming from this blobby region around the black hole. Certainly, if you change the electron thermodynamics, that's what this R high parameter is. If you change the electron thermodynamics, then what you will see is that you change the shape of this region slightly, but it all looks approximately like this. And I would say that the majority of emission in this case is actually not coming from the midplane, because it's not exactly clear what you mean by the midplane of the MAT simulation. So this is a qualitative point that I actually think is quite important to stress for understanding what MAT emission looks like. But again, you have these filaments that are falling onto the hole. And the filaments have kind of these hot surfaces that are going all over, so these filaments are going all over in space, and you're seeing those hot structures. So it's not like you have this steady midplane emission. This contrasts with the same case where, we saw in the MAD case, the emission looks approximately the same no matter what you do. Of course, here I'm just showing you a particular model, but that statement is robust to looking at multiple different models, looking at, in fact, all the models I've seen for MED7 systems. Right, but the SMAD statement contrasts with the same statement where if you shift the electron thermodynamics prescription, you can really shift where the emission is coming from. And so here in this panel, third panel, it's a particular prescription for the electron thermodynamics for the same, you really do have a lot of emission coming from the midplane. There you actually have a disk, it's hot, you see it. If you change the electron thermodynamics, you can shift the emission out into the jet region, and you see.
George, for each of these pairs, it's the same underlying gas density and everything. It's just to change the R high parameter.
No, so for each of the pairs, yes.
For each of the pairs.
So for this, that's a good question. Yeah. So I've taken the exact same fluid description, and effectively I've changed the amount of energy that I, so my fluid description has an overall temperature for the fluid, or an overall internal energy for the fluid. And I need to somehow partition that into energy associated with the electrons and energy associated with the ions. And so this R high parameter controls how hot effectively the electrons are. So now I want to briefly talk about how the story becomes even more complicated by looking at what happens if you vary the gas composition. So I talked about taking made me clarify, thank you, taking the same exact GRMHD fluid description and varying the electron thermodynamics. But what happens if I change the gas composition? So take the same simulation and I say, okay, it has the same number density and so on. Or sorry, it has the same mass density in some sense, but I change from fully ionized hydrogen to fully ionized helium. Of course, there's an entire spectrum between these two, which you can study, but this is kind of just a simple, quick exploration. And so quantitatively, the upshot of this comparison is that when you change the composition, the gas composition from hydrogen to helium, you end up going from 1 nucleon per electron to 2 nucleons per electron. And that changes the way you partition this energy between the electrons and the ions, because now you have twice as many ions in some sense for the energy to go to, which in practice means that you change the overall ratio of temperatures across the domain. So when you swap from hydrogen to helium, it's not like everything just gets hotter. It's some parts get hotter by a little and some parts get hotter by a lot. Overall, the sense is that the fluid has to be hotter in order to reproduce a target flux observation. So at the end of the day, right, we want to match an observation. We know the observation has 0.6 Jansky or whatever, Jansky. So we want to match the observation. So we vary, the number density and so on. But when you vary the number density, you're also varying the temperature of the gas in different ways in different parts of the simulation, which means at the end of the day that the part of the flow that you're seeing can end up varying. So what I'm showing you here again are just these emission maps for 100% ionized hydrogen versus 100% ionized helium. So again, for the same underlying fluid flow simulation, you can go from seeing the kind of jet disk boundary down to seeing the midplane. And if you don't believe me, or if you want to see this in a kind of pictographic quantitative sense, what I've done here is I've plotted the emissivity at a fixed frequency for different values of the temperature of the electrons on the x-axis and magnetic field strength on the y-axis. So what you see is that if you increase the temperature by a different amount in different parts of the domain, you increase the magnetic field strength by the same amount, you will end up crossing different numbers of contour lines. We can talk about that more if you care to, but it's not particularly germane to the rest of the talk. So now here we come back to the variability question that is connected to what Shep asked. I guess, but before I go to the variability on the right-hand side, I'll just again say that in general, helium models are hotter than the hydrogen models. They have lower overall number densities because of this temperature difference and overall lower magnetic field strengths. Now, this is not a categorical statement, it's a qualitative statement, but it tends to be true. It tends to be true. Here, I'm just showing you for hydrogen and for helium, those plots that I showed earlier on, so full polarized information. If you look at these long enough, there's nothing surprising here, so I won't dwell on them. But the point now that I want to make is that I think it's interesting with respect to variability is that because when you change the composition, because you're looking at different parts of the flow, and different parts of the flow have different dynamics, at the end of the day, that means you can end up having different variabilities. So what I've plotted over here on the right-hand side is this so-called modulation index, which is kind of like how much you're like for the light curves at 230 gigahertz for different models with hydrogen versus helium. And the modulation index, or I've plotted the log, the natural log. The modulation index is something like how much the light curve varies over time divided by its mean value. And so to slightly more quantitatively answer or respond to your question, Shep, a lot of these points are very close to each other and pulled from very different models. So the variability totally from different models can end up looking very, very similar. Again, depends on how you measure it. One thing that I think is kind of interesting here, this is a rather busy plot, but one thing you can see is that the MAD models all lie below, or not all, but mostly tend to lie below this dashed line, which is on the side of helium is less variable. So if you swap to the helium, composition is less variable. And the lower R high, or the R high 1 same models also lie below that line. And so this is completely consistent with the 3D representations I was showing before, where the low R high same models kind of have this midplane emission, or at least not emission along the jet walls, will qualitatively all have the same trend for their shift in variability compared to the MAD models, which again don't have a lot of extended features out of okay, great. So I've hopefully given you some evidence for my statement that it's a challenge to account for all of the theoretical uncertainties in the gas composition and electron thermodynamics. If you just tweak these parameters slightly, you can get very different emission sources. You can get the images looking different. You can get different variability properties. But we still want to identify the effective spin on the magnetic field. We still want to, see space-time pulling these magnetic field lines. So, how can we do that? Maybe it's not even possible to exactly measure what the magnetic field lines are doing. So maybe we could, instead as a proxy for this frame dragging of the magnetic field lines, we could look at frame dragging of plasma in the near horizon. So I want to take a quick kind of side journey or whatever, and now argue that even though there's a lot of uncertainty associated with these observations, there is not reason, or we shouldn't give up hope. There is reason to believe that there's something deeper going on. Maybe humans haven't understood about that. So I'm going to talk about machine learning, which may be a dirty phrase or maybe not a dirty phrase in your minds. So I'm going to hopefully convince you that at the very least, this machine learning application is scientifically interesting. But if you disagree, I'd love to talk with you after the talk. So, of course, you have these convolutional neural networks, which are great at performing these classification tasks. Is this image a cat or a dog, for example? So what we did is we took our tens of millions of black hole images, fed them into a convolutional classification neural network, and asked the neural network to predict the spin of the underlying simulation. And there's one part of this slide that I really want to draw your attention to, and it's what this arrow is pointing at. So let me explain in a bit more detail. So what we did was we took simulations from 5 different black hole spins. So high spin, prograde, retrograde, plus minus 15/16, intermediate spin of 1/2 plus minus and 0, and fed these 5 different spins with varying different electron prescriptions into the neural network, different inclinations. And then we asked the neural network what it thought about a spin it hadn't seen. And so for example, I'll give you the example of the 1/4. So again, we fed in plus minus 15/16, plus minus 1/2 and 0. And then we asked it, well, what do you think about this 1/4 simulation? And the network said, I don't know. It said, I don't know what the spin is, but I do know it's between 0 and 0.5. And I think this is incredibly interesting. This is where I think, at least personally for me, the utility of machine learning is really evident, because evidently the machine is picking up on something, given that I've passed in a set of GRMHD simulations. Of course, maybe those GRMHD simulations aren't representative of the real world, but even in a set of models for GRMHD simulations, relatively low resolution, where you can't really measure, for example, the asymmetry of the ring, there appears to be some feature that's secularly changing with the black hole spin. So it says, okay, well, I know that this is indicative of 0 spin. I know this is indicative of 0.5. I'm somewhere between those two. I think that's really, really interesting. Yeah.
So George, this algorithm,
Yeah.
You trained it with 0 plus minus 0.5 plus minus 0.94. When it returns an answer, it's not constrained to give those
That's right.
numbers.
It's a flow between the
It
two
is
guys.
allowed to
That's
flow,
right.
use its own imagination to
That's right.
interpolate something.
Yes.
Okay, good.
Yep. Yeah, I know that is a good point. Yeah.
Did you give it polarization?
Not this.
Okay.
2020. So ancient history. Yeah. So okay. This is interesting, but ideally we want to not treat the neural network as a black box, and instead we want to look into it. And one of the ways you can do this is by studying so-called feature maps. And so basically the way convolutional neural networks work is you take an image and you apply convolution across the image, and you pick out certain features. And so the way that you do this feature map comparison standardly is you look at what that first layer or what the nth layer of the convolutional output is for your neural network, given an input image. And in particular, you look at the output before training and after training. Right? So ideally, over the course of training, you've learned what the important features of your image are. So by comparing these convolutional maps between or before and after training, you can kind of see what the neural network has learned. And in this case, what you find is that the neural network is picking up on these kind of spiral arm features, these low intensity spiral arm features that are in the images. And this is the part 2 of how I think neural networks are particularly useful, because they can identify trends maybe we didn't know about, and then you can actually interrogate them. So it's not like they're actually a black box. You can still learn something. Now, exactly what these structures mean, I don't know, and we'll talk about that on the next slide. But still, neural networks, if anyone hates neural networks, I hope I've convinced you that it's at least worth reading the papers occasionally. All right, so, we still have to do the physics. We still have to understand what these spiral features mean. And so here I've just proposed a few possible examples in the particular context of connecting the spiral features to the Blindfolded effect, and in particular connecting it to the plasma dynamics in the near horizon region. So there are instabilities associated with strong magnetic fluxes, there are instabilities associated with shear layers. These all lead to matter entrainment, for example, and can end up producing spiral arm features that you may end up seeing at the end of the day in these observations. In the interest of time, I'm going to go to the next slide, talking about relatively the same thing. And I want to caveat this slide and the next slide with the fact that this is a work in progress. So in fact, I saw this movie on the right for the first time last night. So do with that what you will. But So we've learned from the neural networks that maybe these low surface brightness spiral features are really, really interesting. So what I've done on the left here is I've produced a very, very high resolution black hole movie. And so the base resolution of this movie is the so-called 4K standard, which is 2160 by 2160. And then I've adaptively refined it to be about 3,000 times better in each direction. And this is a slow light movie with for people who care 0.1 m cadence of the GRMHD and of the images. So I'm still waiting for the angry email from the person whose computer time I used to do this. But one of the things I want to point out about this movie that I hadn't really appreciated before is that if you look in this region inside of this curve, if you look in here, there are little knots of plasma that heat up, become bright. You can follow them in. There's some kind of structure in the spiral arms. And going back to a point that Ramesh made earlier, you may be concerned that this is the effect of floors, or that these may be numerical artifacts. I am going to stake a claim that I actually do not believe that they are numerical artifacts. And some of my evidence for this is that, in fact, while I've only seen this movie for 12 hours, I've seen this movie for a few weeks. And I've produced different versions of this movie from using different GRMHD codes, using different floor prescriptions, using different spins, using different electron thermodynamics, and so on, and they're always there. So I don't know. I can tell you where they're coming from in terms of the simulation. I think that they're not coming from floor regions. I think they're very interesting. I'd love to be able to track them because, again, this goes to the question of whether or not we can see the effects of the frame dragging, if not on the magnetic field, then on perhaps the plasma structure.
George,
yes.
Yeah, super interesting. Do you have any chances of magnetic reconnection in this super high resolution simulation, or?
There's numerical reconnection, but no, there's no explicit treatment for the reconnection. Yeah, so.
I'm not sure those that actually did this magnetic reconnection using very high resolution, did they use a slow light approximate like tools or
so
fast light?
You're probably talking about parts
Yeah.
stuff. Yeah. So as far as I know, they haven't imaged. Actually, I don't know. Do you know?
That would be a project for us then, using your slow light. I mean, the reason that I'm saying is that you already are seeing something that they are seeing that, and then that superposition of this super high resolution ray tracing versus the simulation, that would be super intriguing to have.
Yeah, I totally agree. So just maybe to back up and provide context, I don't know if everyone knows what Raz is talking about, but you can add different physics subgrid models into your fluid simulation. One of the things you can include is magnetic reconnection, which may produce certain signatures. And it would be interesting to compare, for example, these high resolution slow light runs, what you would see.
Sorry, one last question. I wanted to know, in your slow light, is there any washing out of the sequential polarization? Because I know today we were talking with Kaushik, the actual discussion I should definitely continue with you, and we were saying that there is a wash out of the sequential polarization for the plasmoid case. So do you think that super high resolution would actually open up any possibility that they could locally cancel out each other, the flows that are in the opposite direction?
Yeah, so I totally believe the argument you just made, but I'm not comfortable staking a claim right now. I don't know. But yeah, no, that sounds reasonable.
Yeah, I'm thinking whether it's useful to do so now or wait till later. But first of all, this movie is beautiful. The age is really, really nice.
So are you talking about the one, because the one on the right I haven't talked about.
They're both very nice. But maybe I'll just let you talk with the one on the right.
Yeah,
before I ask questions.
So on the right, what I've done, right. So let me back up and say, okay, so this is a slow light movie from a GRMHD, a full three-dimensional GRMHD simulation. But there are a variety of reasons why you might not want to use your 3D model. One of which is that the problem of inverting from a two-dimensional image, even a time series, into a three-dimensional map of emission is a challenging one. So maybe instead you want to invert from your 2D time series image into a midplane model. And so what I've done for the right is I asked the question at every point in the midplane, what is the emissivity that would be required for a two-dimensional midplane model to exactly reproduce the structures of the full three-dimensional simulation. So for those of you who care, this does not obey any of the conservation laws. This is just an effective model for what the midplane structure has to be, what the midplane emissivity would have to be in order to produce a photorealistic movie. One of the things that I think would be very interesting to do with this, again, I've seen this for 12.5 hours, is to, for example, try and decompose this into a whole bunch of different spiral arm features. So I've been told I should talk to Angela about this. But one thing that I found, so I've seen frames of this movie before, and one thing that I think is true, at least overall, if not in detail, is that you can decompose this into a set of kind of 3 primary components. Each of the components is a spiraling structure, but the pitch angle for the spirals is different. So there's some relative power. Anyway, yeah, that's I don't know, Dom, do you want to come back to the question?
No, I'll revisit later.
I want to quickly advertise some work that's being done with some people over at Princeton University.
So,
yeah,
George, maybe very quickly.
Yes.
You said it was slow light.
Yes.
Does it make a difference?
Oh, yeah. So, well, what do you mean by difference?
If you just did fast light.
So this would look very different. The thing,
Okay. Fair enough.
Right.
Fair enough. Yeah.
I think at least, so one of the motivations for this project was to try and understand whether the statistics that are required to produce turbulent realization of this, right? So you can just produce a Gaussian random field and multiply it by something, with particular covariance, and try and reproduce this exactly. And I think one of the questions that I personally want to answer is whether the statistics of those of that generation procedure vary in some secular way with the black hole spin, which of course it should, because what's going on there is set by the black hole spin. So this is to the frame tracking question. And so I think at the very least, those statistics will matter in detail. Now, if there's a statistical trend versus spin, it probably doesn't matter too much because, right, there's just some mapping effectively. Right, so you could. So again, I think we should talk offline because it's complicated, but there's a single look back time for every single pixel. So there is a transformation you could write down. It's just reshaping this data. It will give you the associated proxy for the associated fast light simulation. The one place that differs, again, in detail, if maybe not overall, is that each of these intensities corresponds to kind of like an integrated emissivity along the way. So if you pass through the midplane at some time, then you pass through another point at another time, you'll get different statistics. But I think overall, the statistics end up being the same. So very quickly, I'll just advertise this work. Again, so Alejandro Avendaño is a postdoc at Princeton University. Zhu is a grad student, and Alex Musaska is soon to be a professor. Currently, well, I guess he's currently, he's also at Princeton. And so what you can do, again, one of the hopes would be to come up with some statistical description of these models and then just immediately plug them into just a mapping between your midplane model and the image plane, and you can come up with very, very high resolution movies. This is something. Okay. I have 5 minutes for 10 slides. So I'm going to go very quickly through these slides and then wrap up hopefully very quickly. This is just a set of animations to remind you what you're looking at when you look at a black hole. Or a black hole image. So what I've done here is I've just put a camera very, very far below the image, traced back all of the pixels that make up that image, and put a planet with relatively low density in the middle of the screen. The region you see on your image that corresponds to the planet corresponds to where the light rays hit the planet. And what I can do is I can now turn on general relativity, which effectively means I'm increasing the density of the planet. And unsurprisingly, when I turn on general relativity, I start to bend all the light rays around the object. And so the set of light rays that fall onto the object surface increases. And then what I can do is I can take the object and I can start to spin it. I'm going to give it angular momentum. It's going to spin counterclockwise. and apparently no movie. So that's great. Okay, saving some time. And what you kind of like fill up. And so what you end up seeing is that the image overall shifts over to the right. The paths become more complicated. This will become important in the next slide. But again, the point of this is that because you have a massive object, light gets captured by the black hole. And so there's this critical boundary between geodesics light rays that don't fall onto the surface of the black hole at some point in the past, compared to those that do fall onto the surface of the black hole. This is some kind of critical boundary. And any light ray that follows exactly that boundary is going to orbit around the black hole. So you can kind of now invert the picture in your mind and ask, okay, so suppose I have a flash of light that happens somewhere near the black hole. Well, because I know that it's possible for light rays to orbit around the black hole n times, what I'll end up seeing is I'll see that flash of light multiple times, multiple instances of that flash of light over time, where the delay associated with each of those different imagings corresponds to the path length of my bound orbit. And so that's what you're seeing over here is just some from Kodoro Moyama, a light curve associated with a hotspot around the black hole. And you see that there's this echoing period. Of course, in the real world, if you have non-zero black hole spin, you don't just have circular orbits, you have spherical orbits that are bound. So I'm just showing you some here for, I think, a spin of 3/4 black hole. The upshot here is that each of these orbits has a different path length. It's at a different location radius, which means that it will have a different echo delay. Each of these echo delays maps to a different position along the critical curve. Turns out you can do the math. And so then what you can do is you can say, okay, so suppose I have a flash of light that I set off near my black hole, and I measure versus time what I see at each of these different positions in my image. There will be different echo delays, the position-dependent echo delay. And so over here on the right, I'm just showing you these same maps, but what I'm going to do is I'm going to vary through all the different black hole spins you can have, and then all the different inclinations that you can have. So again, the vertical axis is just your position around the black hole critical curve, and then the horizontal axis is the time delay associated with when you would see an echo. In brief, I will note that all of these different.
Where exactly do you set off the flash?
Yeah, so
that's not a variable here.
That's not a variable in this movie. I have another movie that I believe is in backup slides that I am going to skip for now. But the time delay doesn't matter.
Doesn't care. Okay.
Exactly.
Good.
Now, which ones you will see cares. So maybe you'll only see echoing down here. You won't see echoing of a different period. So the echoing is this universal signature. You can then ask, okay, well, is it actually possible to observe this, right? So certainly you see some echoes, but it's, maybe the echoes are confined to this region, blah, 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 blah. So the first thing I did was I put a hotspot. I just flashed this Gaussian blob. Actually, it was in a Keplerian orbit, and I varied the position of that hotspot. But this is a particular instance of that. And you can see that, in fact, yes, you absolutely can see this echoing period for that hotspot model. You can see different parts along the ring. That's what these different colors are. Echo with different periods. It's cool. You can make a measurement. You could then argue, well, that was a hotspot model, but hotspots are not really representative of GRM, of like the full 3D turbulent plasma. So here's an example of the full turbulent 3D plasma. I flashed it on for a second for 2 GM over C cubed. And then I plot what happens in movie versus time. So for a high spin observation, looking down on the image, you can still see this echoing. And I don't know if you'll be able to see it here, but the glimmer signature corresponds to, for this inclination, brightness here, it spreads out along the ring. And kind of the delay at which it spreads out along the ring changes over time. And that's the glimmer signature. Then my last movie is saying, okay, so now suppose that I'm not looking straight down on the hole, right? So that those, in this animation I showed over here before, going through different spins and inclinations, what you saw is that it could become very complicated. Then you can ask the question, okay, so if I'm now looking at it from edge on, or nearly edge on, can I see any of these echoes? And from the light curve, at least, it's hard to tell what's going on. But if you look at the movie, you can still see that there's this glimmering signature. There's still some structure. And so one of the ways then that you might try and get at that is to compute not one light curve, but 4 light curves corresponding to the 4 different quadrants. And if you do that, you can again see that. So for a bona fide GRM HD simulation, with it's still a model, but still for a full 3-dimensional distribution of gas, not just a hotspot in a particular location, you can still see this echoing period. I'm not an observer. I don't know exactly how to measure this thing, and there might be better ways to try and make this measurement. But at the end of the day, I think that this is, at the very least, an interesting thing to look at as a way to measure spin. Because again, remember, these delay periods are set by the structure of those closed orbits, those bound orbits, and that structure changes as a function of spin. So, all right. I sped through my final slides very quickly, so I apologize for that. But here's my brief summary. I think that it's probably almost certainly true that supermassive black holes, some anyway, power relativistic jets via the BZ process. I want to come up with definitive observational evidence of BZ, which means measuring spin and getting some constraints on the magnetic field structure, or at least frame dragging near the black hole. Horizon scale images have offered a way to constrain things. We saw that with the AHT. But the analysis is mired by significant theoretical uncertainties associated with plasma composition, thermodynamics, and so on. But there's hope via various different possible signatures. Thank you for your time. I'm happy to listen to questions or talk to you later.
Thank you, George. Really a great talk. Maybe a couple of quick questions.
Okay.
Yeah,
I've already asked many. This glimmer is great. It looks like the perfect poster child motivation to do time-resolved imaging.
Yeah.
Right?
Yeah.
Because what you've shown is just the light curve doesn't do the job, because it may look flat, but it's coming from different parts in the image.
Yeah, exactly.
If you could actually get good movies, yeah, that's it. It's perfect.
Yeah.
Sure, that's it.
Well, so it's not like you would get, so this is for a flash on, flash off of the GRMHD simulation. So it would be more complicated to extract this from the time
Right.
series.
But real imaging will go beyond 4 quadrants, right?
Yeah.
We'll have, in our dreams at least, we'll have a lot of information.
Yeah, and in fact, if you were to continue to break this up into more and more quadrants, these signals would become sharper and sharper.
Exactly.
So for Saturday star, that's the whole duration of that is about an hour or so. No, well,
20 times the number.
Yeah, 5 minutes.
Just like 20 seconds.
5 minutes, yeah.
Yeah, so, wait, so it's 100, so I can't.
I would say the period is about 15 M.
Yeah, well, for this spin.
100 times 20
So-
seconds.
So this is 2000
Okay, yeah. Okay.
seconds.
So it's sub-hour. Okay, so you've got to take like minute snapshots.
Yes, but I mean, this is a hard thing to do. This is my pitch
That's
for
why it's
people.
a hard thing. We like hard things.
Okay, well, I won't say it's impossible because then people won't be interested, but it's very hard. which may also be your specialty, so I'm happy. But you want to, we can talk about it in more detail. It's not like if you take, an hour worth of second cadence measurements, you'll see this. I think you want to do something more complicated. It's more complicated.
What is hard? Because the plot makes it look very easy.
Yeah, so the way that I generated this plot. No. This is good. The way that I generated this plot was by taking a fully turbulent 3-dimensional fluid simulation and turning it on. So this is not what happened in the real world, right? But I just turned it on and left it on for 40 seconds and then turned it off. That's not what happens in the real world. But if you do that, then you can clearly see the echo, right? Because once 40 seconds has elapsed, there's no more emission coming from the base flow. But in the real world, you don't turn it on and turn it off. You have this slowly varying thing. And so what you're actually going to see in the real world is like a convolution of these guys with some time series associated with it.
And that's actually, that's the term variability project that, that we're hoping to pursue. But something that is super interesting for me that you mentioned is that is this going to give you some information about the black hole spin?
Yeah, so
That's fantastic. Having just said that, we know that flux actually itself may not be sufficient, at least for M87, to give you any information about the spin. They have to go through the polarization. So that's really cool if you can just, you can just do some light curve analysis. So M87 with some clever treatment like yours and just extract that. I would love it to happen, actually.
I would love it too.
You super promised, yeah.
I think that there is a significant amount of observational analysis that has to be done, because I don't really know how to extract out this, because again, turning it on and turning it off 40 seconds later is completely fixed. So you have to kind of detrend and do some kind of autocorrelation or Fourier series.
May you welcome to a project that we are doing with Shep, actually.
Yeah, so we have a final question from Jonathan, and then we should wrap it up.
Thanks very much, Fabio, and great talk, George. Thank you. I'm parachuting in from the ether outside and coming at it from an observational perspective. And actually, my question I thought might be a little preempted by what Ramesh asked, but I don't think so. From a more open-ended perspective, I mean, I was really interested in the comparisons of the M87 EHT observations that are published with your theoretical simulations, and then you did that with the intensity images and with the polarization images. And in a completely open-ended way, if those observations were to be improved in some practical way, which direction would you want to push in? Would it be the time resolution and first, right? Would it be the time resolution? Would it be improved angular image resolution? Would it be lower resolution features combined with high resolution structure? Would it be improved polarization precision, improved polarization sensitivity? Where would you go first?
So I will answer from my perspective.
That's all I'm asking for.
Yeah. I would really like to see high fidelity images with increased dynamic range before other things, to be honest, because I'm really excited by these small scale structures that we're seeing in this high resolution movie. And I think that having any handle on those, seeing those in the real world would mean that we're actually seeing probably plasma instabilities in like transrelativistic plasma around supermassive black holes. I think that you'd want to measure them in the polarimetric properties of those guys. I think that such a measurement would excite our plasma physics colleagues, which is always good because it would help us kind of better understand and bridge the gap between these theoretical models and kind of what plasma physics or plasma physicists say should be happening. So that's my March 21st answer.
Yeah. So I have to ask you, you're saying seeing that substructure in the ring, but isn't that higher angular resolution than we have as well? Or is it just dynamic range that's in it, you think?
So this is structure in the n=0 image. Certainly it also shows up in the n=1 thing. So yes, you do need higher resolution, but I don't think you need sub micro arc second resolution. I think if you had on the order of a few micro arc seconds and you were sufficiently clever in your deconvolving the beam algorithm, I think you can still say interesting things. So I don't think you need to really resolve these things in sharp detail, but I think you want the dynamic range and you do want better resolution.
So a few micro arc seconds, of course, is easier said than done, but I think by saying improved dynamic range, you're pointing to sort of super resolution techniques in a way. It comes to the same thing. Thank you so much. Really appreciate it.
So we actually have a very fast question from Maciek. He promised it's a yes or no question. So
hi, George. Very nice talk. I'll make it yes or no question because Fabio asked me to be quick. So for this neural network model that you presented, did you validate it by feeding it something that is not from, you know, the same sort of GRMHD setup, like with a RIAF snapshot or with some very different numerical setup?
So with very different numerical setup, yes. And that's actually what you're seeing in the middle panel here. But not, so all of the things that we fed it were, for validation purposes, were from GRMHD, with the exception of we ran it on the actual M87 data as well. But all of the training and validation stuff was done on GRMHD. Very different GRMHD, but still all GRMHD.
It would be fun to do that.
I agree. I agree.
Yeah. Okay. Thank you.
All right. Thank you, George.
Terrific, George. Wonderful.